In this video, I'm going to show you how to use the calculator to obtain confidence intervals for a population mean using the normal distribution. I'll be taking a couple of examples from section 9.1, and I think you probably find this a lot easier to follow if you join me in the text. I'm looking first at page 469, and first up we have number 24. Problem says as follows. Simple random sample of size n is drawn from a population that is normally distributed, with a population standard deviation sigma known to be 17. The sample mean x bar is found to be 123. Part A reads, compute the 94% confidence interval for mu if the sample size is 20. Now we use a built-in function for this on the calculator. You would find it by going to the stat menu, and you go to the test submenu, and number 7 is the one we want. It's the z interval. This is a confidence interval that's based on the normal distribution. So we can select that by pressing 7. And you can see it has two modes here, data and summary statistics. For this problem we don't have data, so we want summary statistics. Sigma is given in the problem as 17, so we'll key that in. X bar is given as 123. N is 20. And the confidence level is 94%. So at this point we're ready to obtain the interval, and it's right there. Now, in this view, we can see the interval as a lower limit and an upper limit, but there's another way to view this, namely as a point estimate plus or minus a margin of error. And it's nice to be able to go back and forth between the two. So if you were asked in this case to determine the margin of error, the easiest way to do it would be as follows. We take the upper limit, which is 130.15, and we're going to take the difference between that and the lower limit, which in this case is 115.85. And we're just going to cut that distance in half, the difference in half. And that gives us the margin of error. Now the interval is centered on the sample mean, which is 123, so another way you could describe the interval would be as 123 plus or minus 7.15, and of course 7.15 is the margin of error. This is not requested by the problem, but it's helpful to know that. Anyway, part B is asking for basically the same thing, except now the sample size has changed to 12, and they want to know how it impacts the interval. So let's go back to the stat menu, go back to the test menu, and go back to the z interval. Everything is the same except for this sample size. So we'll change that to 12, and then we'll calculate that. Now you can see that the interval gets wider, slightly wider. In fact, if you wanted to calculate the margin of error just to compare, the last example, the margin of error was 7.15. So in this case, if we take the difference and cut it in half, we'd have 132.23, and we're subtracting the lower limit, which is 113.77, and then taking half of that. So our margin of error is now 9.23. So one of the things we definitely want you to pick up is that if you decrease the sample size, you are going to cause the width of the confidence interval to increase because there is greater uncertainty based on the small sample. Anyway, part C is asking compute the 85% confidence interval. So let's go back to the stat menu here, back to z interval. And in this case, part C, sample size is back to 20, but the confidence level is down to 85%. So let's change what we need to change here. And we're ready to calculate. And you can see the interval there, 117.53 and 128.47 for the limits. Now they have a follow-up question here, and they say, how does decreasing the level of confidence affect the size of the margin of error? Well, let's calculate it. Probably be helpful to have it. So in this case, we want to take 128.47 and subtract 117.53 and divide that by 2. So the margin of error is 5.47. So just to reiterate, first margin of error we got, confidence level of 94%, sample size of 20 was 7 and some change. When we decrease the sample size, we got a larger margin of error. Part B, margin of error was 9 and some change. And now when we decrease the confidence level, keep the sample size at 20, we're also seeing a decrease in the margin of error. Part D is asking, could we have computed the confidence intervals in parts A through C if the population had not been normally distributed? And the answer is no. And the reason is that the sample size is too small. 20 and 12 are too small for the central limit theorem to really apply unless the parent distribution is itself known to be normal. So if it's not, then it's garbage in, garbage out, and you can't apply the central limit theorem. Finally, part E is suggesting if an analysis of the sample data revealed one outlier greater than the mean, how would this affect the confidence interval? Well, you got to remember that the mean is not resistant. So in other words, if you have an outlier that's to the right end of the data set, it's going to shift the mean to the right, and it's going to cause the center of the confidence intervals to shift. It is also going to widen the margin of error a little bit, and so you're going to have a wider interval than you would otherwise have without the outlier. So just to reiterate, make sure you're tracking us here. If you decrease the sample size, you increase the width of the interval. If you want to make the interval narrower, you would increase the sample size. It's kind of contrary to most people's intuition. Likewise, as far as the confidence level is concerned, if you increase the confidence level, you are going to cause the interval to be wider. And if you decrease the confidence level, you're going to cause the interval to be narrower. Again, that's also contrary to most people's intuition, but that's the way it is. Now for the next example that we're looking at here, we're going to go to the next page. So this would be 470, and I want to do number 36. Now 36 has a data set attached to it, and I've got that data set already keyed in, so let me just clear this here. And part A, well, let's read it first of all. 36 says retail milk prices. To estimate the national average retail price for a gallon of reduced fat 2% milk, an economist surveys 20 stores in cities from across the United States and obtains the following data. Treat these data as a simple random sample of 20 retail prices and answer the following questions, assuming that sigma is known to be 0.46. Part A is asking, use the data to compute a point estimate for the population mean retail price. Now, we could get that as part of the process, but since they're asking for it explicitly, the easiest way would be to get it using the one variable stats. And if you'll notice, I've already got the data keyed in list 1 just to save some time. So I'd go to the stat menu, I'd go to calc, and I'd hit one variable stats, and if you recall, it defaults to list 1. So we just press enter, and right there you can see X bar. That's the point estimate that they're talking about, 3.549 and some change. Part B is asking, because the sample size is small, we must verify that the price is approximately normally distributed, and thus, or that the sample does not contain any outliers. The normal probability plot and the box plot are shown next. Are the conditions for constructing a Z interval satisfied? Yes, they are. If you look at the normal plot, you can see that all of the data values are within the boundary lines there, which we typically look for. It's not the most linear looking plot that I've ever seen, but it's linear enough for our purposes. And the box plot, it's not totally symmetric, but it's symmetric enough. So moving on to part C, it's asking us to construct a 95% confidence interval for the mean price of reduced fat milk, and then interpret the interval. So what we can do is go to the stat menu again, and we go back to the test submenu, and we're still using a Z interval here, but this is now a data-driven problem. So we change that to data, press enter to select it, and now you can see what it wants. It wants to know, first of all, what's sigma? Well, it was told to be in the problem there is 0.46. So we'll go down there and put that in. And the data is indeed in list 1, and the frequency is 1. Don't ever change that. The confidence level, we were asked to find a 95%, so we need to go down and change that to 95%. And then we're ready to calculate that, and the interval is right there. Now, as far as the interpretation, there's several ways to explain what the interval represents, but probably the best way would be to say something like the following. We are 95% confident that that interval that you see right there from 3.35 to 3.74 contains the true mean retail milk price. Part D is asking, construct a 90% confidence interval for the mean price of reduced fat milk and then interpret that interval. So go back to the stat menu. And all we have to do is go back to the Z interval and change that from 95% to 90%. Calculate. Interval is right there. 3.38 to 3.71. You can see it's a bit narrower, as we would expect. And so as far as interpreting the interval, we can say that we're 90% confident that the true mean price of milk is contained in the interval from 3.38 to 3.71. Finally, part E is asking, what happened to the width of the interval when the level of confidence is decreased? Well, you can see that it got narrower. And it's contrary to intuition, but for a lower level of confidence, you're basically covering less variability. A higher level of confidence needs to cover higher degree of variability. Probably the best way to see this is to look at that Java applet that I assigned to you guys to go along with confidence intervals. When you run that, you can see a stack of confidence intervals, and you can see that probably a good way to explain what a 95% confidence interval would be is that if you take 100 random samples from a certain population, on the average, 95 of those confidence intervals will contain the true mean, and 5 will not. Now, that's on the average. We're not saying it's going to happen every time. It's the law of large numbers. But anyway, that's another way to explain what a confidence interval is. So if you have a narrower interval, you have less of a chance of capturing the true mean, but it will be narrower. And if you have a wider interval, you have a better chance of capturing the true mean, but it will be wider. In the next video, we'll show you how to do the same thing with a t-distribution.